Good morning, good afternoon, good night, whoever is watching this. What is up, guys? Hey, Devs is back. Don't mind my hair. I did just wake up. I didn't just wake up. I woke up about 2 hours ago, but now it's 7:30. I did another assignment that was due tonight. So after I got out of the way, I was kind of woken up, ready to record, and I was looking at LeetCode problems, and currently we're doing some linked list problems. It's about the only ones I'm doing. And we looked at the next LeetCode problem, and I thought I would be able to solve it, but it is a hard problem. Now, mark this in the books as the first hard problem I have solved. But we're going to go ahead and get into it, and I'll try to the best of my ability to explain it. But my solution is fairly, it's definitely not the best solution, but I'm going to type out my solution, and then we're going to look at the solutions tab and kind of compare mine to probably the most known algorithm for this, right? And so this is problem 23, merge k sorted list. You're given an array of k linked list. Each linked list is sorted in ascending order. So we're given an array of linked lists, right? So these are multiple linked lists, and then we have to sort them into one complete list. The linked lists are 1 to 4 to 5, and then 1 to 3 to 4, and then 2 to 6, and then merging them, they expect it all to be in ascending order. So this one's fairly complicated. It just it took a little bit of mental power and a lot of variables, don't get me wrong. So k is equal to list links. K is in between 0 and I think that's 10,000. Yeah, 10,000. The list I.length, so the actual length of the list is between 0 and 5,000, and the actual values in the linked list are between negative 10,000 and 10,000. List I is sorted in ascending order. The sum of list I.length will not exceed 10,000. Okay. So for this solution, I kept a few integers. So we're gonna do int cur lowest, and we're gonna set that to negative 10,000. And then do int next lowest, and we're gonna set that equal to 0. Next lowest, and we're gonna set that equal to 10,000, right? So current lowest will keep track of the lowest value we have found, and then we're gonna loop over the first node in each list, and then while that current node is next is equal to the current lowest, we're going to go ahead and return or add it to our list, right? So I think the first pass finds the current lowest, and then it switches to the next lowest, and then each pass will find the next lowest until the end. So we want to loop while we'll go ahead and give all our initialization to that. So we're going to create a boolean, and then all null is equal to false. And this will keep track if we have, if every list in our node is null, then we know we have sorted it correctly, and we want to break out of our while loop, right? And then we need some list nodes. I'm going to call it head and iterator, and then we can set head equal to iterator, and then that's going to be equal to a new list node. Okay, and then after the while loop, we want to return the head.next, right? And then while all not all null, we want to loop through all the lists, right? So there's one value we want to keep, so we're going to keep up with a null count. And this is going to loop, so we also need a for loop to loop through the list. So int I is equal to 0, I is less than list.length, and then I plus plus, right? So we want to see if null or if list dot I is equal to null, or we want to see if it doesn't equal to null, we want to go into the loop, else we want to increment the null count, right? So null count plus plus. And then, so right now we haven't iterated or implemented the actual sorting, but what we have done is we have the null count, and then whenever all the lists are equal to null, we will end up having the null count be equal to the list.length. So if null count is equal, if null count is equal to this length, then we want to set all null equal to true, because this is saying we're keeping up with the count of all the lists that are, or the linked lists that are null, and then if the null count is equal to the list.length, then we want to set all null equal to true, and it will break out the while loop and return the head. Okay, and then in this if statement is where we're actually going to add the sorted list. So we need to see if, or we want to do a while loop, right? So say the current lowest is equal to 1, and there's 5 ones in a row. We want to go ahead and add all 5 of those ones into the array, or into the list, right? So we need to check that list, let's turn that to list, okay, not QList. List of I is equal to null, not equal, yeah, not equal to null. And list of I dot value is equal to the current lowest, right? So while it's equal to the current lowest, we can go ahead and write the values, or sort the list. But we need to make sure that we have a proper current lowest. So if list I does not equal null, and we also need to set the next lowest. This is equal to 10,000, right? At each loop of the iteration, so we can actually find the lowest, right? So if that's not equal to null, and list I dot value is less than next lowest, we want to set the current value to the next lowest. So next lowest is equal to list of I dot value, right? And then after we break out of the for loop, we want to set the current lowest equal to the next lowest. So what we have right now is a while loop that checks a boolean all null. If for when we go through the for loop, if all of the linked list inside of list equal null, then null count should be equal to list.length. And then if that happens, we know that all of our lists are null, and we can break out of it and then return the next head, right? So yeah, so when this is set to true, it breaks out of the list. Now for the for loop, we're checking each linked list in the list, right, in the array. For each list in the array, we want to see if it's null. If it's null, we increment the null counter. If it's not null, we go inside the if statement. And then we check while list of I does not equal null. So this is saying our list isn't null. Just so we can the reason we check this is so we can access this value. And then list I.val is equal to the current lowest value that we have found. Then we want to add that into our list. So we can do iterator.next is equal to list I. Right, and then we want to increment the list of I is equal to list of I dot next, and then we also want to increment the iterator list node. So iterator is equal to iterator dot next. Okay, and I think that should be good. We can go ahead and run it and see if it works for the test cases down below. Without syntax errors, no counts, no count. Oh, we set an assignment variable instead of the equivalence logical operator or the assignment operator anymore. Might not have been initialized. That's right. So we want to set null count equal to 0, even though Java does set each every item you create equal to its null equivalent, which for integers is 0. You want to go ahead and set that equal to 0. And yeah, so we can walk through this again. We set a current lowest equal to the lowest value we can find, which in this case is negative 10,000. And we set next lowest equal to 10,000, right? Because that's the highest value we can get. We keep a boolean called all null equal to false, and this is able to loop through the linked list until all are null. That's what we want to do. When all are null, we know we have iterated through each list to the very end, and we want to break out of it, right? We create two list nodes that are head and iterator. We set head equal to iterator and equal to a new list node. So this is our this is the start of our list, or head.next or iterator.next will actually be the actual sorted list. Iterator is the one that goes through the list we're creating and goes ahead and adds the next value, right? And then we loop for while all are not null, and we set int null count equal to 0. So we want to see if null count ever equals list.length, and if it does, we know that all the lists are null. We set next lowest equal to 10,000 each time, so we for sure will find the lowest next value. And then this is the for loop that we want to check. So this checks each linked list in the array, right? And we can go ahead and kind of, I feel like it's a bit more readable if you break that up a little bit. So we're going to loop over each linked list in the list. And then we need to check if the list we're looking at currently is equal to null. If it's not equal to null, we'll go ahead and check to see if it's equal to the current lowest. And if it's not equal to if it's equal to the current lowest, we want to go ahead and add that to our list, right? And then next we'll check to see, once it breaks out of this while loop, we know that either it's null or the value of the list is not equal to current null lowest anymore. So then we go ahead and check if the value that we have now is the next lowest, and that will happen for each of the values that aren't equal to the current lowest in the list, right? And then next lowest is equal to list I.val. So this is the value we are actually checking for the next lowest. And because if the value held at the list currently is less than next lowest, we want to go ahead and set next lowest to the lower value, right? And then if the list is actually null, we want to go ahead and increment the null counter, right? And then we set the current lowest equal to next lowest, because this went ahead and looped through every list, looked at the value that's not equal to current null or current lowest, and it goes ahead and sets the next lowest for us, right? So we have current lowest equal to next lowest, so the next time we go through the for loop, we'll go ahead and add all the current lowest values to the list. And then we go ahead and check if null count is equal to list.length, then all null is equal to true. And once we break out of this while loop, we know that we have our sorted array, and then head.next will end up returning that array, right? Or that linked list, sorry. And it works for all the test cases down there. Let's go ahead and submit it and see what we get. There we go, 4 milliseconds. It beats 78%. So my solution isn't horrible, but it looks like the average is actually 2 milliseconds of runtime when ours is 4 milliseconds. So I don't think that's that bad. And we go ahead and check the solutions tab. We want to see a Java solution. Initialize a min heap, priority queue, compare it is based on a node value. Add the head of every non-null list into the heap. Create a dummy node. This acts as the head of the file merged list. Head processing, complexity, and log k. So we'll go ahead and take a look at this value. So he creates a priority queue, and then he sets a new priority queue. This is a comparator, so this is what checks what the priority actually is. For list node list in list, if list is equal to null, continue. So that goes to the next iteration. If it's not null, we'll go ahead and add the list into the priority queue. List node answer is equal to new list node 0. That's kind of what we did here. We set it equal to a dummy node, and then you return answer.next. While the priority queue is not empty, list node current is equal to priority queue.poll. Dummy is equal to next. Current. If current.next is not equal to null, pq.add current.next. Dummy is equal to dummy.next. Okay. So ours is a little bit more complicated, of course. Ours uses straight integers, booleans, and the list node. We didn't use any data structures, but the priority queue solution is pretty nice. I don't know too much about priority queues or heaps. I do know the basis of them and how they work. But basically, every list that's put into it is compared based on its value with others' list value, current value, like the front of it. So no matter what, the priority queue.poll will give you the lowest value in the first nodes of all the lists that you have stored. So it sets dummy.next equal to the current. So that's storing the lowest value. That's kind of like what we do here. Iterator.next is equal to list I. Their dummy is our iterator, and it's equal to the current value. And then if their current.next does not equal null, so that's so then that adds the next value inside of the array if it's not null. And then dummy is equal to dummy.next to implement it by 1, or increment it by 1. So ours is definitely a little bit more complex. Ours purely used list and kind of some primitive data types instead of using the priority queue solution. But the priority queue solution makes it a lot cleaner, makes the logic easier, right? And so yeah, that's not too bad. So we could have used the for list node list in the list for our for loop. It would have made all of this code cleaner instead of having list I everywhere. Yeah. I think the n log k space complexity is okay for the priority queue. See, but our solution beats 78% as well. Yeah, 78.17%, and that solution beats 78.05. So ours actually has a better time complexity. I mean, it just runs slightly faster. And the only reason for that is probably for the priority queue overhead, because in order to, you have to sort the priority queue every time you add an element. And so that takes a little bit of time, versus ours is just checking and setting the current lowest. But ours has some unused loops, if that makes sense. Like, the first loop doesn't really do nothing except grab the next lowest and then set the current lowest into the next lowest. Because if there's no values that equal negative 10,000, then it won't add anything into our list. And then the next iteration, it will find the lowest value. And if the lowest value is only contained into one list, then we won't add any other value into our list, if that makes sense. So you have like 40 linked lists, right? And only one of them holds the current lowest. Then we're only going to add the current lowest of one linked list, and then the next iteration. So worst case scenario, I think it's n times m, where like m is the size of the or the average size of the list, I would say. Because saying if you assume that each value is different and that each list is equal to like some really big number, or the list size is some big number, then it will have to go through both of these loops for each value, right? So it ends up taking a while. But I'm not sad with the solution. I'm very happy with it, pretty proud of it. First hard problem, did it by myself. Now the solution that he gave is a fairly nice solution. I need to kind of touch up on all of the Java data structures that they provide and how to use them properly. And the more we do of those, the more we can intertwine the data structures with each other, right? Because Java has a list, because they have their list interface, right? Why is that? Oh, that's gonna bother me. Why did my tabs not? Okay, anyways, we can just leave it like that. They have their list interface, and then you cannot type. You pass it the value or object that you want, so you can also have a list of list nodes, kind of like what we have here. And then we can call that list of lists, and then that's equal to, you can call their linked list interface, or linked list class object, actually, of list nodes. And this implements a linked list like we have been studying or working on here, but it's Java's implementation of it. And they also have priority queue, they have sets, they have heaps and maps and just all types of stuff. So priority queues are useful for a lot of different algorithms. Like later on, if we ever do Dijkstra's algorithm, the priority queue is very useful for that, because you want to find the shortest node, or the closest node to the current value, and you constantly loop over the distances, and then you add like all solutions, and then the priority queue will give you the shortest path, so you can go ahead and check the shortest path. And I haven't done the Dijkstra's algorithm, shortest path algorithm in a long time. I did do it for a assignment in my data structures and algorithms class at the very end, but yeah, I'm not sad with the solution. The priority queue solution is definitely more concise and a bit easier to understand than what I did here. But I think for using primitives and just the list node interface or list node class, fairly good solution. It does beat the solution we looked at, but his is easier to understand, right? But yeah, I think that's gonna be it for today's episode. I think this video's already running a little over 30 minutes, or close to 30 minutes. So I'm probably gonna leave this here, and tomorrow, of course, we're gonna do some more LeetCode. I might not do a hard problem. Probably one or two more linked list problems, because I'm having fun with linked lists. They're not too terribly hard to wrap my mind around, but like I said, on day 14, I think we're going to switch it up, go to a different data structure or an algorithm, and do a couple problems involving those, so we can really expand our minds, like I said, and learn something new. And we're going to try to become pretty proficient at it. But until then, y'all stay safe, stay healthy. I'm going to chill on the couch and probably watch some anime for a little bit, and then I got some math homework to do. But I will catch y'all in the next video. Be sure to like and subscribe, and leave any suggestions y'all have down below for any problems you want to see, or if y'all want to see any projects for me to work on. Y'all can give suggestions, anything like that. I'm currently trying to learn JFrame for Java so I can create small applications, and then hopefully the end goal is to learn Spring Boot so I'm able to work like in an enterprise setting, because that's very valuable to a lot of companies. And then LeetCode is to ace the interview questions, of course. But like I said, y'all stay safe, stay blessed. I will catch y'all on the next one. Hey Devs is out.